Swayam Prabha. Digital India. Educated India.
Okay, so then there is one more popular result we can quickly find, that is the result of finding the centroid of a triangle, right? So centroid of a triangle. Okay, so the result says show, well, we need to show this result. Show that the three medians the medians of any triangle meet in a point which divides each of them in the ratio 2:1, right? Show that the three medians of any triangle meet in a point which divides each of them in the ratio 2:1, right? So what are the medians? Well, medians are the points, well, these are the line segments joining any vertex to the opposite midpoint, of the side. So let me call this as my triangle ABC, and the moment we introduce these 3 points, let us say these 3 points, they have position vectors with respect to some origin, as let us say OA, vector OA, which is vector A, and then the position vector of B is vector B, and similarly the position vector of C is vector C, right, with respect to the origin. And now we have a median which originates from any vertex, and it divides the opposite side at equal ratio. So that is the median, right? And the result asks us to show that, look, these three medians, they meet at identically the same point, and this point is in such a way that the medians are divided in the ratio 2:1. So this is what we have to show, right? So this is what we have to show, that the point of intersection is common and it is such that the medians are divided in the ratio 2:1. Okay. Now, so what do we have? So let us say, as I have just started, let us say my position vectors of the points A, B and C, A, B and C, well, are given by the vectors A, B and C, small letters, right? And let me take one of the medians, and let me say that the end point of the median is at point P. So which means the P is dividing BC at equal ratio. So we can use the previous example's result, that the position vector OP, is given by the ratio. Using the ratio is going to be B plus C by 2, right? So that is from our previous result. So then, so this is what we have. So now, so what do we have? We need to find for this vector AP, for the vector AP, right? We need to find this position vector, sorry, we need to find this vector x, where x is, well, we need to find this vector x which is ox, where my point x is given by this this median point, right? So basically we have to find this median, this point x. So what we have is, now what we have is that the position vector x, so notice that the position vector x divides AP in the ratio 2:1, right? So it divides AX ratio XP is 2:1. So we are again going to use the result that my position vector x is given by well, so let me call this point P, this OP to be denoted with vector small p. So notice my notation is, all my points are denoted by capital letters and all my vectors are denoted by small letters. Okay, so now the position vector of A using our previous result is, sorry, position vector of x using our previous result is, x is given by the ratio 1 times the position vector of A, which is OA, plus 2 times the position vector of P, which is OP, divided by 1 plus 2, which is 3. So now we can see OA is the position vector A, and OP is, using our result that we have found, is 2 times B plus C by 2 divided by 3, right? And what we have is that this position vector of x is A plus B plus C by 3. So we have found the special point x, which is dividing the line AP in the ratio 2:1, and the coordinate of the special point x is this following. Now we can repeat our exercise, repeat our exercise to find x using the same method on line, let's say BQ, on BQ, or on the third line, let's say CZ, right, and on CZ. And we will see that the position vector of x will be nothing but the permutation, it will be the permutation of A, B and C. So the first gave you A plus B plus C, and the next result will give you B plus C plus A, and the third one will give you C plus B plus A. So essentially what I am saying is, whether you had taken the line AP or the line BQ or the line CZ, you are going to get the position vector of x all the same in the 3 cases, and hence we see that the position vector of x which divides these lines, these median lines, are the same, and hence the centroid is the common point of intersection. So we have, so what do we have? The result is, what I am trying to convey is that the centroid is common. The centroid is common, which has the position vector given by this quantity that we have just found, right? Okay, so that completes the problem here, that the centroid is common and such that it divides the median lines in the ratio 2:1. Okay. So then, without proving, I am going to state one more interesting result. The result says, so this one is in the form of a theorem. We call this as the so-called bisector theorem. Bisector theorem. Again, most of these results are in basic high school algebra, if I must say, and I'm just recapping some of these results, very interesting results, and will be used in solving more complicated problems later on. So what do we have is, the result says that if we have a triangle, some triangle let me call this triangle with the name OAB. So let us say we have a triangle OAB, right? And the bisector of the angle AOB meets the line AB at point P, right? So bisector of the angle, let me call this angle OAB. So it bisects the angle in two equal angles. The bisector of this angle OAB meets the line AB at point P. So the result says that we have, so what we have is that the ratio AP over PB, is the same as OA over OB. Okay. So when I'm talking about these quantities AP, PB, I'm not putting any lines on top of these quantities, which means I'm talking about the magnitude of these vectors. When I do not have a line on top of these quantities, which means I'm talking about the magnitude. So what this result says is that the ratio AP over PB is the same as the ratio OA, this result OA over OB. And that is what the bisector theorem says. Okay. So again, listeners can quickly, find the proof of this result starting from the two problems that we have done previous to this result. Okay. So then I have some other properties for other properties of these vectors which are important. So we will list all of these. Listeners can quickly see that these are very basic, so I'm not going to go into the derivation of these results. So scalar product. So these are some properties of scalar product. So suppose I have A and B, they have representations OA and OB. They have representations OA and OB. Then what I have is that A dot B, so A and B are the vector representations of OA and OB. Then A dot B is the magnitude of A times the magnitude of B times cos of theta. Right? And then what, so this is my famous dot product law, where theta is the angle between the two vectors, A and B, right? So what we have is some results related to this dot product is that the order in the dot product does not matter. Whether you take the product A is to B or B is to A, it doesn't matter. And then what we have is A dot with B plus C is A dot with B, that's the distributive law, plus A dot with C. Right? So the first one is my commutative law, and then the second one is distributive law. Okay. So then what I have is lambda times A dot with B. So that is, I should write as follows. The bracket should come here. So the scalar multiple of A times B is lambda times A dot with B. Right? So we have associative with, so this is associative property with scalar multiplication. So associative with scalar multiplication. Okay. Then we have the so-called property about the magnitude of a vector. We talk about the magnitude of a vector to be the dot product of the vector and then the square root, right? So the magnitude of the vector is the dot product. So which tells us the fact that the dot product actually gives us scalar quantity. If you take a dot product of two vectors, it's a scalar. And then we have that two vectors, the dot product of two vectors is 0 if either A is orthogonal to B. Notice the sign I have used, the notation I have used. This means perpendicular. Perpendicular. So either A is perpendicular to B, or what I mean is when theta is 90 degrees, this particular theta I am talking about, right? Or A or B, one of the vectors is 0, right? And then then what we have is then other results are, well, how many? Well, this is number 6. So my other results are I suppose my this set I, J, K are my set of orthonormal vectors. Orthonormal vectors, orthonormal bases. Then I dot I is equal to J dot J equal to K dot K. Well, these are unit vectors, so you expect that this dot product will be 1. And because these are orthogonal vectors, unit vectors which are orthogonal, so we get that the following dot product I dot J is J dot K is K dot I. These are all 0. Okay. So then the result says that suppose we have two vectors in 3D and we can represent these two vectors using these orthonormal bases as follows. Let's say this is lambda 1 I plus lambda 2 J plus lambda 3 K. And let's say the second vector is mu 1 I plus mu 2 J plus mu 3 K. Then I can define my dot product only in terms of these components lambda i's and mu i's. We see that these are my my dyadic products. Right? My dyadic products. Okay. So then what we have is there are some very easy examples. Let me just state these examples and listeners can quickly do it for themselves. For example, a quick way to check all these properties is look at this following example. So suppose a vector A is given by 2I minus J plus 2K and B is 4I minus 3K. Then we can quickly, the problem says find the magnitude of A and the magnitude of B and the angle between them. Angle between them. So when I say angle between them, you have to find theta, which is A dot product with B divided by the magnitude of A times the magnitude of B. Right? So that's the very quick example, and I leave this example at this point. Okay, so then there is another interesting result in the form of a theorem which I have decided to prove as well. So the result says the result is in the form of a theorem known as the so-called Apollonius theorem. Apollonius's theorem. Okay. So what it says is, suppose we have, let me draw the triangle first and then it will become easier. So we have the triangle OAB and let me say that M is the midpoint. Okay. So now the theorem says that let M, the point M be the midpoint, of this line segment AB, and we have to show, well, the result says that we have that OA square plus OB square is equal to 2 times OM square plus 2 times AM square. Okay. So that is what the result asks us to show. So that could be very quick based on our previous results. We see that the midpoint, the midpoint M has a position vector OM. So this is my quick proof. My position vector OM is given by, will be given by the position vector of A, which is A plus B by 2, right? And then we see that what have we got? So OM is A plus B by 2. And so what we have is, from here we can find what is OM square. So OM square is, well, we can find 4 times OM square, right? So 4 times OM square is A plus B dot product with A plus B, right? Or sometimes I call this as, using our previous property, this is also the magnitude of A plus B whole square, right? We can open up this dot product using our distributive law, and we see that this is the magnitude of A square plus the magnitude of B square plus 2 times the magnitude of A dot product, 2 times the dot product of A with B, right? And now we have that. So we have found what is OM square. Similarly, we can find what is AM square. So AM square, AM is nothing but half AB, because M is the midpoint. So we have M being the midpoint of this line AB. So from here we can find that 4 times AM square is AB square, or this is nothing but the magnitude of, so AB is B minus A. So this is the magnitude of B minus magnitude of A, magnitude, OB minus OA whole square. And from here we have B square plus A square minus 2 AB. And then what we have is that if we add, well, if we add this result, let me call this as 1 and let me call this as 2. If we add these two results, we see that we are going to get our result, that 2 OM square plus AM square is going to give us, so 2 times OM square plus 2 times AM square is going to give us the magnitude of A square plus the magnitude of B square, which is nothing but OA square plus OB square, right? I think we have a square sitting in the result itself. Okay, so that's what we have. So adding 1 and 2. Okay, so that is what we have. And then let me now talk about another important concepts which we'll be using later, that is the so-called projection of a vector. So what is this projection of a vector? So projection of a vector. Okay, so we have, suppose the component, this is typically the projection of a vector is the so-called component of a vector along the direction where we are trying to find the projection. Okay, So let me write this. So component of the vector v in the direction a, which is given by v dot a hat. So component of the vector v along the direction where we are trying to find the projection, that is the direction a. Now, so this is also equal to v dot with a divided by the magnitude of a. We just need the direction of a to make this projection. We don't care about the magnitude. So we have taken the unit vector a. Okay. So that is my projection of v along a. So I call this as my projection of v along the direction a. Okay, so notice this notation. Okay, so then, so what have we got here? So let's look at a quick example. So suppose our vector v is given by lambda I plus mu j plus nu k, right? So we see that v dot I is given by lambda. V dot I is lambda. We take the dot product and we see that the projection of the vector v along one of the axes is equal to the value of the component, right? We take the dot product necessarily, okay? And similarly, you can check, well, quickly you can check that this is equal to mu and v dot k is nu, and so on. Okay, so that quickly ends the ideas of projection.